Okay, hello and welcome back to Chemistry Talk. Today I'll be finishing the discussion on equilibrium reactions and we'll be um, talking about chemical equilibrium. But one quick note before I continue with the lecture is to be sure to subscribe to my channel. When you subscribe, I create more videos, more content. Also, if you have any questions about the material or any requests for new material, you can leave that in the comments section as well. So, regarding equilibrium reactions have that double arrow here indicating that they can go in the forward direction, which is your typical reactant to product, or they can go in the reverse direction, meaning you're going from product to reactant. An equilibrium law, meaning the equilibrium constant, how to find that is we make an equilibrium expression where we take the products, the concentration of the products, and we divide it by the concentration of the reactants. So Kc here is the equilibrium constant for the reactions, and this bracket here indicates their molar concentrations. So there is a significance to this K, this Kc. When we have a very large equilibrium constant, there's more products than reactants. Therefore, the equilibrium is far to the right, meaning you have a shift to the right. You have a lot of products. When K equals 1, the concentrations of the reactants and products are equal or are nearly the same. And when K is very small, we have a small amount of products and we have a lot of reactants. So the equilibrium would lie far to the left. So K is considered small when it's less than 10 to the negative 3. So that's the general rule. Now, this slide, I'm going to switch to pen mode now. Um, This slide talks a lot about manipulating equilibria. So there's three main rules. One, 2, and 3. So rule 1 says that when the direction of an equation is reversed, the new equilibrium constant is the reciprocal over the original. So in this first equilibria, we have nitrogen gas and hydrogen gas, and we form NH3 gas. The equilibrium constant is 4.5 times 10 to the negative 9. But when I switched the reaction to go into the reverse direction, I took the reciprocal of the original equilibrium constant to find the new equilibrium, meaning I took 1 over the original. It's the reciprocal. So that's the first rule. The second rule is when the coefficients in an equation are multiplied by some factor, the equilibrium constant is raised to the power of that factor. So here I have this same equation here, but what I've done is I've multiplied the entire equation by 2. So you see I have a coefficient of 2 here. I multiplied the hydrogen gas by 2 to get 6, and I multiplied the NH3 gas by 2 to get 4. So I raised the equilibrium constant to the second power to get the new equilibrium constant for this reaction. And the third one is that when we add chemical equilibria constants in a multi-step reaction, you just multiply the previous constants. So if I have 3 steps here to get to my final reaction, I would just multiply the 3 Ks to get my final equilibrium constant. That's similar to Hess's law in thermochemistry, but this one's not used as much as the other two. Now, there is one more part of equilibrium, chemical equilibrium, and that's the reaction quotient Q. And Q measures the amount of products and reactions present during a point in time in the reaction. Now, a lot of people or a lot of students get confused between K and Q. And the difference is that K is a constant. It doesn't change, while Q changes depending on the concentration of the reactant. So by comparing Q and K, we can determine the direction of a reaction. So we also have some rules when we're comparing Q and K. When K is greater than Q, the reaction proceeds from left to right, meaning the reactants are too high and we have more reactants than products. When Q equals K, that's good. The reaction is at equilibrium. And when Q is greater than K, the reaction proceeds from right to left, meaning there's more products than reactants. Okay, so I think I have 4 examples here The first example says for the reaction between nitrogen gas and hydrogen gas to form ammonia, I mentioned that reaction before, the following equilibrium concentrations were obtained. So we have a 0.01 molar nitrogen gas, 0.05 molar of hydrogen gas, and 7.5 times 10 to the negative 8th molar of ammonia gas. And I have the equilibrium reaction here. So I'm asking for the equilibrium law and to calculate Kc. So the equilibrium law would be that product over reactant. So our equilibrium law would be the concentration of NH3. Now this is going to be squared because we have 2 moles in the reaction over the concentration of nitrogen gas, and there's no superscript there, so we leave it alone, times the concentration of hydrogen gas, and this is cubed because there's 3 moles in the equation. So that handles part A. Part B wants to know the equilibrium constant. And to know the equilibrium constant, we would just plug in what we know. So Kc would equal the concentration of ammonia gas, 7.5 times 10 to the negative 8th, and this is squared per the equilibrium law, over, divided by the concentration of nitrogen gas, which is 0.01 molar, times the concentration of hydrogen gas cubed per the equilibrium law. So we're just plugging in what we know. So Kc for this reaction, on my calculator, it would equal 4.5 times 10 to the negative 9th. So that is Kc, and this is the equilibrium law. Okay, which of the following statements is true? So we're looking for a true statement. Switch to red. Q does not change with temperature. That's not true. Q does change with temperature. It's temperature dependent. The equilibrium constant does not change with temperature, whereas Q is temperature dependent. No, that's not true. Q is not temperature dependent. It just changes with temperature. And Kc could also change with temperature as well. K does not depend on the concentrations or partial pressure of reaction components. It does depend on that because the equilibrium law, you're putting in the concentration, so that's not true either. Q does not depend on the concentrations or the pressure of the reaction components. That's not true either. It does depend on that as well. So that means our final statement would have to be true, and let's see if it is. Q is the same as the equilibrium constant when the reaction's at equilibrium. Yes, that is a true statement. Okay, third example. How is the reaction quotient used to determine whether a system is at equilibrium? The reaction quotient must be satisfied for equilibrium to be achieved. No, that's not true. At equilibrium, the reaction quotient's undefined. No, that's not true. The reaction is at equilibrium when Q is less than the equilibrium constant. No, that's not true. The reaction's at equilibrium when Q is greater than Kc. No, that's not true. But the reaction is at equilibrium when Q equals Kc. Okay, here we are given a reaction. Oxygen gas and nitrogen gas form 2 moles of nitrogen monoxide. We're given the concentrations at a certain point in time, and we're asked to calculate the Kc for this reaction. So Kc, I'm going to write the equilibrium law, would equal the concentration of NO squared divided by the concentration of oxygen gas times the concentration of nitrogen gas. And those have no superscripts. So if we're looking for the equilibrium constant at these concentrations, it would be the concentration of nitrogen monoxide, which is 4.7 times 10 to the negative 14th, squared, that's a times there, divided by the concentration of oxygen gas, 0.0078 molar, times the concentration of nitrogen gas. So it's just plugging in what you know into the equilibrium law. So when you do this division, you're squaring your concentration of nitrogen monoxide and dividing that by the concentration of oxygen gas and the concentration of nitrogen gas, and you get the equilibrium constant, Kc, to be 6.9 times 10 to the negative fourth. So I hope this helped you to understand chemical equilibrium. In future videos, we'll be discussing acids and bases.